Okay, welcome to physics. This is going to be a shorter video. We're going to talk about a couple of the questions on that worksheet 1.05. Well, the first one is we've got a barrel, it says, right? And that barrel is at theta of 52 degrees. Do you agree with that? Okay, so we have an acceleration. So we have 670 meters per second. And that's our final V, right? Okay, so what you notice, this says, the question says, the force and the acceleration is constant. It says, what is the force that acted on the projectile? Okay, so maybe you guys got this right, maybe not. But I'm going to tell you right now, that is a summation of forces. How many of you did that in this way, as a summation of forces? In other words, the question is, what are the forces that are involved here? So, did anyone consider the forces? Now, I know what you did. You said A equals V squared divided by 2x. Isn't that what you did to figure out acceleration? And then so you got your acceleration, and you multiply that by your mass of the projectile, and you got a force. And that's what you put down for your answer, right? Which, in reality, that is true as the summation of forces that cause this mass to accelerate. So all that math is right. The summation of force answer is right. But what if I asked you, what's the force of the explosion on the gun? Could you further describe that? So that's what I want to get to here. So think about that and answer me. Yes. Thank you, Sage. That is true. It has to be greater than that. Okay, now can you tell me why it has to be greater than that? So we're down here. I'm going to get rid of this 52 for a sec. And I'll just call it theta just so a little bit easier. We're down here. We got a ball inside the barrel. What are all the forces on the ball? So I want you to draw a free body diagram of the forces right now. Okay, so what you guys know for sure, absolutely without doubt, there's a force of gravity on this, right? And we can say that there's a force that's way bigger than this, that causes, so this would be the force of explosion that's causing this thing to move, right? What are the other forces? So those are the two that you know, but what are the other forces that you didn't think about?
Is there a force in the number because it's on the surface, or is it technically not touching the surface?
No, there would be a force of normal. There would be a force of normal too. Now this one would be way different, probably because, there's probably going to be some loss of pressure and stuff in there, so it might be actually floating. I'm not sure how we would talk about that one. But yeah, there's another way to think about it. What else is going on though? Friction, okay. So we're going to have friction. In what direction is friction going to be? Yeah, friction will be in that way, and it'll be pretty big, right? How about this force of gravity? How does that relate to this explosion force? Does that have anything to do with it? Well, yes, okay, can you explain? Yeah, there's going to be, so if you take this force of gravity vector here, there's going to be a portion of that gravity that is, down the ramp. Or we can actually do math with it down the ramp. The real force is really just down. Well, we can do math with this part of that gravity if we do that right triangle. Okay? So, in order for this ball to move up the barrel, the first thing it has to do is get bigger than that. Okay? So if you think about the summation of forces that are in this, so the summation of forces is going to be the force of explosion, okay, plus, because summation is always plus, right? Plus the force of friction, plus, and we're just going to be talking about the forces that are in line with this force of explosion, because you can only go one direction at a time. So the force of normal doesn't really count here, although we'll find out later how it affects the friction. But So force of explosion plus force of friction plus, what else we got here? We got the force of gravity that's down the ramp. Okay, well, maybe I should do a big F for that. So there's a force of gravity down the ramp. So this is the summation of forces. Now let's put in the signs for this. This would be a positive because it's going to go that way. This would be a negative, and this would be a negative. Okay? So we start out our summations with this, it's always a summation, but since these are all vectors, then really this is actually a negative direction, and this is a negative direction too. Okay? So in this case, the summation of forces then causes the mass to accelerate. So the best answer for this would be, you could put some numbers in here. So let's just say that you got a force of, okay, so you kind of redrew the ball here. So we have the summation of forces in the direction of the explosion is going to be the force of explosion. So that's going to be the big one right here, right? Okay. And then we're going to have minus the force of friction, and we'll call it kinetic friction. Okay. And then we're also going to have minus, so friction we'll say is in this direction, and then we're going to actually have, so if we have force of gravity here, this part, so I'm going to say minus the force of gravity down the ramp, and we would then rewrite this as a summation of forces equals the force of the explosion minus the force of friction minus sine theta mg. Okay, so this right here then is the part that we can actually add into our force. So if I was going to ask you what was the force of this cannon, then I got to know what you guys get for your answer for the summation of forces. So you guys got something like 9,000 newtons. That's your summation of forces, because that's what's. Okay, so this isn't what you get in the actual problem, but let's just say your summation of forces is 9,000, and that summation of forces caused this ball to accelerate over this displacement. And so 9,000 isn't, though, the total force of explosion, or the force that the cannon puts on the ball, because we have to overcome these other forces first. So 9,000 is a summation. That equals the force of explosion, which is what we're going for in this case. Regardless of what the question asks you or not, I want to teach you this right now. Minus the force of kinetic friction, which we cannot determine in this case. But we can determine this. So we have sine theta mg. So we have the sine of 52. And what was the mass of that ball, people? Okay, so the mass was 75 kilograms, so we have 750 newtons. Okay? So if you solve for then, finally, the force of the explosion, it's going to be 9,000, or whatever your number is, plus the sine 52 times 750. Okay, give myself a little more room here. Plus the force of kinetic friction, and that finally equals the force of explosion. Okay, so even simple questions seem to be less simple, or maybe more simple, because you're actually figuring out what's going on. Do you have another question about this worksheet? Anyway, I want to make sure you did this one right too. Okay, so it says, right, draw free body diagram of this system, it says, right? Okay, so force of gravity, right? Force of tension. Was there anything else in there? Yes, there is, because if it says system, then we might have to include what other forces are happening here. Yes, that's correct. So there's a force. This string here is going to be forcing on the wall. And how big is that going to be? as long as the string is massless? Well, it's going to be the same as the force of gravity. Do you agree? So that's going to be the force of tension on the wall. So when we talk about tension, it's the force that's put through a string or a rod or something like that. Okay? So where's the other, is there another force? Well, it's not normal, but it's the force of the ceiling, which, well, it's got to be the same length as the force of tension, right? So the force of the ceiling here is going to be equal to the force of tension. Okay, now you say it's equal, but is it really equal? It's equal and opposite, right? So, but it is equal in magnitude. Okay, so on to the other question that we had about the rocket ship. Okay, so you got this situation, right? Okay, so first of all, draw your free body diagram. Okay, who wants to give me the first one? Force of gravity, right? I made that too long. I'm gonna make it a lot shorter. Okay, force of gravity. Okay. What's the other one? The force of the thrust. Okay, so I'm gonna make that one big. Okay. The force of the thrust. What's the other one that you didn't think about? Thank you very much. Friction. Which direction does that go in? Yeah, so you know, the kind of the rule for these free body diagrams is the vector arrow that's representing the force has to touch the object. If you can get it all to come out of one spot, that's good, but in this case, I'm just going to put it here, okay? So this would be, well, it's not very good, but, you know, somewhere there's going to be a force of air until you break through the atmosphere, right? Now, if you didn't get that, then you don't do the math right. Okay, so the question is, you know, what velocity is this after we accelerate for 7.5 minutes at 18 meters per second squared? Well, that should be easy, right? V equals V sub naught plus AT. We assume that it starts at 0. It does, right? So V equals 18 meters per second squared times 7.5 times 60. And we should get a final velocity of, so that answer is 8,100 meters per second. Okay? So I want you guys to draw up the summation of forces here, or better yet, tell me what the force of thrust is. Okay? So draw an equation that tells what the force of thrust is. And include as many numbers as you possibly can. Okay, so we have our summation of forces, and so we just have to put in all the forces. So we have the force of thrust, plus the force of air friction, plus the force of gravity. Okay, so now we're going to draw it with the directions in there. So force of thrust will keep positive. The force of the air is in the opposite direction, so I'll have that as a negative. And the force of gravity is opposite too, we'll have that as a negative. Okay, so and in this case you can actually put in a number here, right, mg, because we have mass, don't we? Now what else? We're going for force of thrust, we said here, so if you just solve this for force of thrust, it's going to be the summation of forces plus the force of the air plus the force of mg. Because you have to, you know, you have to go at least this. If you go equal to those two things, then it floats. Or it just sits there, right? Okay, so in this case, then we got the force of thrust is equal to, now the summation of forces is what causes this mass to accelerate, right? So we can put then, you know, substitute that in, we'll put m, acceleration of the shuttle, okay? M times acceleration, plus the force of the air, plus, now I'm going to put mg here, okay? So our next line is going to look like this. All right, what was the space shuttle mass? So the mass was 2 times 10 to the 6th kilograms. times acceleration is 18 plus force of the air plus 2 times 10 to the 6th times 10. Okay. So the force of thrust then becomes 36, oops, the other 6, or 3.6 times 10 to the 7th plus 2 times 10 to the 7th plus the force of air. And that would be our actual force of the thrust then we needed to achieve that acceleration. Questions about that? Yeah, and thank you very much for bringing that up. This force of thrust here, since we use the average acceleration, is the average force. But a typical rocket thrust pattern is going to be, you know, kind of like this. And then and that would be the force of the engines. Because they need to get going to velocity, because the higher your velocity, the more stabilization you have because of the fins on a rocket. So you try to achieve a fast velocity quickly, and then you have more stability. So all this kind of brings us to that question again, because the question at the end of that, the space shuttle question asks, it says, what's the acceleration at liftoff? Okay. So we know that a summation of forces causes a mass to accelerate, and we're looking for that right there, okay? But before we do that, we need to define the summation of forces. So in this case, the summation of forces then is the force of thrust, okay, and it'll be plus the force of gravity of the space shuttle, plus the force of air. And for this, we're going to cancel out the force of the air because like we said, if you have a force of air velocity curve, it's going to look like this. And right here at liftoff, there's going to be, you know, negligible air resistance. So we're going to cancel that out for now. But they give the force of thrust, and you should be able to determine the force of gravity. So the summation of forces then actually equals, you know, whatever the force of thrust was in that problem. Okay, it says right here the force of thrust is 1.3 times 10 to the 8th newtons. Okay, so we can put in 1.3 times 10 to the 8th newtons. And then really it's minus the force of gravity, right? Because even though it's a plus, because it's a summation, the gravity is in the opposite direction of the thrust. So you have to indicate that with direction with that sign. So if we look at the force of gravity of that, then it says the space shuttle has a mass of 2 times 10 to the 6th kilograms. So it's the force of gravity is going to be 2 times 10 to the 7th. Okay, so it's minus 2 times 10 to the 7th. And then you'll get your actual summation of forces. Okay, so if you take that answer, then whatever those numbers are, you plug them back into this equation. Summation of forces causes mass to accelerate. Acceleration then is summation of forces over the mass. In this case, the summation, or the acceleration, the summation of forces is all this right here, right? 1.3 times 10 to the 8th minus 2 times 10 to the 7th. Okay, and you divide that by 2 times 10 to the 6th. In case I screwed that up, is that the mass? Yeah, 2 times 10 to the 6th. And then you will finally get your acceleration, and I think it was around 55 meters per second squared. And that was just off the pad. Okay, hopefully that helps you guys understand some Newton's laws a little bit better. Have a good day.